Okay, I'm going to do some problems from section 11.8. These are power series. That term power series comes from this term right here. When you have a variable, x, and successive powers. As n goes from 1 to infinity, you go from power of 1 to power of 2, power of 3. So that's the term power series. The goal here is to find the radius of convergence and the interval of convergence. So let's start by noticing that we want to find values of x that make this converge. That's the interval of convergence. It's all values of x that make this converge. Notice first that if x equals 0, that makes it doesn't matter what n is. If x is 0, everything's 0 there, and so we're adding up a bunch of zeros, and that definitely converges. So it gives us the center point of our interval. That's the center. Now what I want to find is the radius. The radius, r, is equal to 1 over L, where L is the limit as n goes to infinity of an plus 1 over an. Just like the ratio test, you're doing essentially the ratio test. You can leave off the x though and just put this part here, the negative 1 to the n. So that gives us limit as n goes to infinity. On the top here I have negative 1 to the n plus 1, and then I have n plus 1 over negative 1 to the n. That's what the an plus 1 over an is. Okay, so this is all equal to limit as n goes to infinity. I have absolute value of negative 1. Those cancel, and then I have n plus 1 over n. And of course the absolute value of negative 1 is just 1, so you can just ignore that, and this whole thing equals 1. So as I said before, the radius is equal to 1 over L, where L was this limit, so the radius is 1 over L, which is 1 over 1, which of course is 1. Okay, so now I've got the center point of the interval. The radius is 1, so I go 1 in each direction. And now I have to check the endpoints. When x equals 1, it's like checking a whole series. So we'll check this x equals 1. We're going to plug back in to the original series where x equals 1. So instead of having negative 1 in x to the n, x equals 1. So it's negative 1 to the n times 1 to the n, which is the same as negative 1 to the n. Okay, and this is an alternating series test, and it diverges because the limit does not go to 0. It fails the alternating series test. Okay, so this diverges by the alternating series test. Okay, so we do not include the endpoint positive 1, and likewise the same is going to be true for the negative 1. When x equals negative 1, we have the series negative 1 to the n and negative 1 to the n. If you like, that's equal to the series negative 1 to the 2n n, which is really the series just n. If this is a power of 2, then it's positive, and the negative doesn't really matter, so it's just a series of n, and of course this fails. This is divergent by the divergence test, since the limit does not go to 0. The same is true up here. You could say that this is, you don't have to say it's alternating series test, you can just say that it diverges by the divergence test. Okay, so the final interval, here we have the radius is 1, and the interval is negative 1, 1. Okay, without the endpoints. Okay. Let's do another one, number 5. Number 5 is a series of x to the n over 2n minus 1, n equals 1 to infinity. This is a good problem to do. Sorry, I'm having technical difficulties here. Kind of new to this particular machine. Okay, same thing. I want to find the interval, so the first thing is let's find the center point. That's 0, and the reason I know that is because when x equals 0, it just makes this whole thing 0, so that's anything around there will be the interval. Okay, so now I'm going to focus on the 1 over 2n minus 1. I'm going to take the limit as n goes to infinity of an plus 1 over an, and in this case I'm ignoring the x for the time being. I'm going to do 1 over 2 times n plus 1 minus 1 over 1 over 2n minus 1, which is the same. When you divide by a fraction, it's the same as flipping it and multiplying, or multiplying by the reciprocal. So what I've got here is, this is really 2n minus 1 over 2 times n plus 1 minus 1. And that is limit as n goes to infinity, 2n minus 1 over 2n. 2n plus 2 minus 1 is 2n plus 1. That goes to 1. So here, my radius, remember this is L, this is the limit of that, and the radius is 1 over L. In this case, it's just 1 over 1, so there's nothing going on there. So there's our radius, and now I've got, so far my interval is negative 1 to 1, but we've got to check the endpoints. Okay, so let's do x equals negative 1. When x equals negative 1, I've got negative 1 to the n over 2n plus 1. And this is an alternating series. The limit as n goes to infinity of 1 over 2n plus 1 equals 0. That's the first part of the alternating series test. The second part is that it's decreasing. I've got 1 over 2n plus 1. That is decreasing. Let's take the, you can take the derivative of 1 over 2x plus 1. That's equal to the derivative of, this is 2x plus 1 to the negative 1, and then I'm going to take the derivative of it. So that's negative 2x plus 1 to the negative 2 times 2 on the inside. So that's equal to negative 2 over 2x plus 1 squared. That is definitely less than 0, because it's negative on top and it's something positive on the bottom. So it's definitely less than 0, which implies that 1 over 2n plus 1 is decreasing. So this passes the alternating series test, so this converges. Negative 1 to the n, 2n plus 1 converges. Okay. Okay, so that's the left endpoint, -1. That converges. And now let's check the right endpoint, x equals 1. That gives us the sum 1 over 2n plus 1. Okay, so here this is not an alternating series, so we need to apply a different test. You could do the integral test for this, or what I'd like to do is just notice that this is really like 1 over n. The highest power is 1 over is a n to the first power on the bottom. So this is like the p series 1 over n, or the harmonic series 1 over n. So I'll write that. It's similar to 1 over n. So what I'm going to do is a limit comparison. Limit as n goes to infinity of 1 over 2n plus 1 over 1 over n. That's the limit as n goes to infinity of n over 2n plus 1. Just flip this and multiply, and that gives me 1/2, which is not equal to 0 and not equal to infinity. And so that means that both diverge. And the reason I know that both diverge is because this series diverges. So when I compare to something that diverges, and I get something that's in this limit that's not equal to 0 and not equal to infinity, then both series must diverge. Okay, so now we're finally done. We can say that the radius of convergence is 1, and the interval of convergence is, okay, what happened? We got that interval, but we found that -1 needed to be included because that caused the series to converge, but +1 did not. So here's our open interval, half-open interval.